Just wanted to start in on the first part of Chapter 2. Chapter 1 was scientific method, and in Chapter 2 we're going to start a lot of this review, for example, scientific notation. We use scientific notation in particular when we encounter very large or very small numbers, and it's just a lot easier. It's a much easier for us to account for it. We don't have to put in a lot of zeros into the calculator, which tends to lend itself to kind of stupid mistakes. And so an example here, so if we were to have, let's say, 310,000. So scientific notation, generally how that looks is we're going to have the first one integer with a decimal point and the rest of the numbers that follow that are integers, 3.1. So 310,000 is the same thing as 3.1 times 100,000. Okay. Also, so then 100,000 is the same as 10 to the 5th. Okay. And so what see then this number 310,000 is identical to 3.1 times 10 to the 5th. Okay. And so what we do then, if we're trying to convert this number into scientific notation, we're not gonna do something like this. So generally what we need to know, where's our decimal point now? There at the end. Where is it going to be? Okay, over here. And since we're dealing with powers of 10, we're essentially dealing with decimal places. And so in this case, all we need to do is convert to scientific notation is count how many decimal places we need to move it over. 1, 2, 3, 4, and 5. So in that case, it becomes 3.1 times 10 to the 5th. Okay? And so do me a favor. So try these ones that are given just to kind of check to make sure that you're comfortable with scientific notation. Pause it for a second and do that, and then come back to the video in a second. Okay, so for 84 million here, so decimal point is there. Needs to be over here, so we're going to have to go over 1, 2, 3, 4, 5, 6, 7 spots. Okay, so we're going to have 8.4 times 10 to the 7th. Okay, so for this one we're going to go 1, 2, 3, 4, and 5 spots. So we're talking about 3.04 times 10 to the 5th. For this one, now we're going to have to deal with small numbers. And for small numbers, same idea, but the difference here. So for example, this one, our decimal point is here, it needs to be over here. So this is the same as 2.81, okay, divided by 10 million. Okay, and then so, which is the same as multiplying by 1 over 10 million. Okay, which is the same as 1 over 10 to the 7th, which is the same as 10 to the negative 7. So when we're dealing with small numbers like that, same idea, we're going to count. This time we're going to count over to the right decimal places, 1, 2, 3, 4, 5, 6, 7. And so because of that, we're going to have 2.81 times 10 to the negative 7th. Okay, and so for this one, we have 6.03 times 10 to the negative 1, 2, 3, 4. Okay, and same thing here. When we're going from scientific notation back to a regular number, we can count over, and if we need to add a digit, we can just substitute a 0 for it. So for example, 4.31 times 10 to the negative 7th. We're going to have to move that over 7 places. 1, 2, 3, 4, 5, 6, 7. And we can just fill those in with zeros. Okay, so this number is going to end up being 43,100,000. And I want you to try these ones as well. So pause it for a second and do it. 2.03 times 10 to the 2nd. We just need to move it over 2 places, so that's the same as 203. Same thing, so similar here, 1.78. Now if we have a number that has a negative exponent, we're going to go back. We have to count to the left. So 1, 2, 3, 4, 5. So it's going to be 0.0000178. and 9.11 times 10 to the negative 7th is going to have 6 zeros followed by the 911. Okay. Important thing with scientific notation, though, is the real issue we have with that is when we get to doing calculations with it. When we use this on the calculator, do not plug it in directly like that. If we're doing a calculation as 3.1 times 10 to the 5th, if we're dividing by that, what the calculator is going to do is say divide by 3.1 and then multiply it by 10 to the 5th instead of dividing it by the entire thing. To help us with that, there's a button on your calculator. If you have like a TI-83, it'll be second comma, which has there's 2 capital E's to it. So instead of plugging in 3.1 times 10 to the 5th, what we do is 3.1, that second comma gives us the E, and then we just put the exponent there. And so what that means is, so this 3.1 times 10 raised to the power of whatever number you put after that. Okay, so if you do this, use this on your calculator, I'll probably have to say this a few more times, you'll prevent any order of operations problems on your calculator. Okay, the other part with that, so that's scientific notation is used for a lot of calculations and measurements, but when we do measurements, there's kind of 2 components to it. Obviously we have a number, but what's important is the unit as well. Okay, and so we have different systems that we use. English system is what we use here in America. The metric system is typically used in Europe, and generally that's what we're going to use in science because, as we'll see, it makes sense. If you don't believe me, try to do a few conversions in your head. English system, you can start with an easy one. So, you know, how many inches are in a foot? Okay, we got 12. How many feet are in a yard? That's 3. Most people know that. Where we start to get to an issue is how many feet are in a mile, how many yards in a mile. Okay, which 5,280, 1,760 for feet and for yards and feet that are in a mile. When we have the metric system, everything is just going to be based on a power of 10. Okay, and so we'll get to that with conversions in a second, but it's just much easier. If you know a few prefixes, you know the entire system. Okay, and so the standards then, so for length, English system, we're talking about inches, feet, yards, miles. Okay, and so for the metric, then we're going to talk about meters and any variation of that. It could be millimeters, centimeters, kilometers, stuff like that. Okay, as far as mass goes in the English system, we can talk about ounces, pounds, and again, just to kind of keep in mind, you know, how many ounces are in a pound. Again, you get a completely different number for your conversion factor than you had before. Where if we compare that to mass, for metric, we're talking about grams. That could be milligrams, kilograms, stuff like that. The conversions are all going to be the same. For time, that's going to be the same. For seconds, seconds for each. Okay, temperature on the other hand, so English system, right? We talk about Fahrenheit. Metric system, we're talking about degrees Celsius. Okay, and just as another point of emphasis in terms of why the metric system is better, think about it this way. What is the freezing point of water in Fahrenheit? That's 32. The boiling point of water in Fahrenheit, that's 212. Okay, again, kind of random numbers with what we have. Compare that to Celsius. Freezing point of water in Celsius is 0. Boiling point is 100. So again, we're going to have much easier conversions. Okay, with SI, what we're going to use, and we'll introduce this later, but Kelvin is going to be important. We'll get to that, the reasons why we need to use that later, and how we convert between Celsius and Kelvin in a bit, and why that's used. And then finally, volume here. So for volume, you can do for this, you know, quarts, gallons, gallons, fluid ounces, stuff like that. Where we're talking about volume for the metric, we're talking about liters. That could be milliliters, that could be kiloliters, and stuff like that. Okay, so when we take a measurement, though, obviously the number that we're talking about is important. The unit that we're using for measurement is important, but we're generally going to have a certain level of uncertainty. Okay, and so that's going to be limited by the precision of the instrument that you're using. So in this case, what I have here, I have an example of a measurement. So we have some kind of ruler here. Let's assume these are centimeters here for a second. And the smallest increment that we have is on the centimeter. Okay, and so this arrow that we have here, let's say we're trying to measure this arrow. Okay, so we can see it's right about there. Okay, and so looking at this, what are we sure of? At this point, looking at this where this measurement falls, we're absolutely sure that it's at least 4, and we're absolutely sure that it's less than 5. So this digit here, the 4, is absolutely 100% has to be correct. Okay. However, it's going to be 4 point something, right? It's not exactly on the 4. It's not all the way to the 5. We're going to have to approximate that. Okay. And so what we do when we take a measurement, what we're going to do is we're include everything that we're sure of. In this case, the 4, and then we approximate one and only one measurement. Okay. And so this one is going to be different. So if depending on who you are, depending on who you ask, you may interpret this a little bit differently. But if we were to look at that, it looks like it's a little less than halfway. Okay, so let's call this 4.3. Okay, and you talk to someone else, maybe they'll see this as 4.4. And so if you can't agree on this digit right here, it doesn't make sense to include something like 3479. You can't say that if you're not even sure about this digit as it is. Okay, so our standard for measurements is always everything that we're sure of, exactly one, at least one, no more than one that we approximate. Okay, and so we'll generally have this on tests where I'll give you a measurement kind of like this, an object with a measurement device next to it. I'm looking for the number, true. Can you see that it's what number it's going to fall at? But also we want to see, do you do it at the appropriate level of precision? Everything you're sure of, one you approximate. So if you were to put 4.3, that'd be good. If you were to put 4.4, that would be good. If you were to put 4.35, that's not good because that's more precision than we can claim based on the instrument. And so the precision of the instrument that we're using to make measurements is going to have a lot of consequences for what we do later on.